For the last 20 years, the global automotive industry has shared a very specific, very cynical inside joke. Whenever a reporter asked an executive about the future of electric vehicles, the executive would smile and say the exact same thing. Solid-state batteries are the holy grail, and they are always exactly 5 years away. 5 years away in 2010. 5 years away in 2015. 5 years away in 2020. Toyota, the company holding the most patents on the technology, quietly pushed their commercial timeline to 2027, and then again to 2028. The consensus among Western and Japanese engineers was absolute. The physics were too stubborn, the manufacturing was too expensive, and the Holy Grail would remain locked in the laboratory. And then, in the second half of 2026, the joke died. Right now, today, in 2026, a factory in China is rolling cars off the assembly line that can drive 1,000 kilometers on a single charge. That is the distance from London to Rome, without ever plugging in. And they are doing it powered by a battery that physically cannot catch fire. Not a prototype, not a concept car sitting on a motor show floor. A production vehicle, built by Geely, utilizing a solid-state cell that achieves 400 watt-hours per kilogram of energy density. This is happening right now, today, in 2026, and it means the fundamental limitation of the electric age. The fear of the fire, the fear of the dead battery, the fear of the charging station is being engineered out of existence. If you want to understand how the country that was supposed to be playing catch-up just solved the single hardest problem in modern chemistry, hit subscribe. It genuinely helps this channel bring you more deep dives like this one. Let's get into it. To understand why a solid-state battery is the most important hardware breakthrough of the decade, you have to understand the hidden flaw inside the device you are using to watch this video, and the C are sitting in your driveway. The lithium-ion battery was commercialized by Sony in 1991. It built the modern mobile world. It is a masterpiece of electrochemistry, and to be fair to the incumbents, it has earned its monopoly. It is relatively cheap. It can be recharged thousands of times, and it packs a massive amount of energy into a small space. But it has a fatal structural flaw, and that flaw is the liquid electrolyte. Picture the inside of a standard lithium-ion cell. You have a cathode on one side, an anode on the other, and a porous plastic separator in the middle. To make the lithium ions move from one side to the other, the entire inside of the cell is flooded with a liquid electrolyte. Here is the problem. That liquid is an organic solvent. It is highly flammable. It is essentially a chemical sponge soaked in lighter fluid. If the battery gets too hot, or if it is punctured in a crash, or if it is overcharged, the plastic separator melts. The cathode and the anode touch. A short circuit occurs. The temperature spikes to hundreds of degrees in milliseconds. The liquid solvent boils into a highly flammable gas, and the cell vents that gas into the air. This is called thermal runaway. A single bad cell can ignite, which heats up the neighboring cell, which ignites, creating a chain reaction that can burn a 3,000-pound vehicle down to the steel chassis in roughly 90 seconds. And you cannot put it out with water. But the liquid electrolyte does not just create a fire hazard. It creates a performance ceiling. Because the liquid is so reactive, you cannot use pure lithium metal for the anode. If you put pure lithium metal next to a liquid electrolyte, it reacts violently and destroys the cell. So, engineers have to use graphite, a form of carbon, to host the lithium ions. Graphite is heavy. It takes up space. It acts like a bulky hotel for the lithium ions, limiting the total amount of energy the battery can store. The absolute physical ceiling for a standard liquid lithium-ion cell is roughly 300 watt-hours per kilogram. So the old problem is this. The battery that powers the modern world is fundamentally capped in its energy density, and it is soaked in a flammable liquid that can turn a car into a bomb in 90 seconds. This felt like a problem with no real solution. You needed the liquid to move the ions, but the liquid was the exact thing holding the technology back, until someone decided to remove the liquid entirely. So here is the question everyone in the industry asked. If the liquid is the problem, why not just replace it with a solid? A solid ceramic, or a solid glass, or a solid polymer. A solid cannot catch fire. A solid is tough enough that you could theoretically ditch the heavy graphite anode and use pure lightweight lithium metal, instantly doubling the energy density. The solid-state battery was the undisputed holy grail. So why did it take until 2026 for it to reach mass production? Why did Toyota, with over 1,300 patents on the technology, fail to ship it? The answer is that the solid-state battery was universally dismissed by manufacturing engineers as a billion-dollar paperweight, and the dismissal was based on 3 specific, brutal physical walls that nobody could climb. Wall number 1. Interface resistance. In a liquid battery, the liquid flows into every microscopic pore and crack, perfectly connecting the electrolyte to the electrodes. Solid touching solid is completely different. It is like trying to shake hands while wearing thick winter gloves. On a microscopic level, the surfaces are rough. There are gaps. The lithium ions cannot jump across those gaps. The electrical resistance skyrockets, and the battery chokes. Wall number 2. The dendrite problem. When you charge a battery with a pure lithium metal anode, the lithium does not always deposit evenly. It forms sharp, microscopic needles called dendrites. In a liquid battery, these are bad. In a solid ceramic battery, they are fatal. As the dendrites grow, they act like tiny chisels, cracking and shattering the brittle ceramic separator from the inside out. Once the ceramic cracks, the battery shorts and dies. Wall number 3. The manufacturing nightmare. To build a solid-state battery, you cannot use the standard factories that build liquid lithium-ion cells. The solid electrolytes are so sensitive to moisture that they must be assembled in dry rooms, where the humidity is kept below 1%. Building a dry room the size of a football field costs hundreds of millions of dollars. The yield rates were abysmal. You would build 1,000 cells, and 900 of them would have microscopic cracks in the ceramic. Because of these 3 walls, the incumbents gave up on near-term mass production. They optimized the liquid instead. They added silicon to the anode. They tweaked the cathode chemistry. They squeezed the last 5% of performance out of the flammable sponge. And they told the world to wait until 2030 for the solid-state revolution. That assumption held for a decade, right up until a group of engineers in China decided that if you cannot break the ceramic, you should stop using ceramic. Here's the twist, and this is the part that changes everything about how we store energy. The Japanese and Korean labs spent billions trying to perfect a pure, rigid, oxide-based ceramic separator. They tried to force a hard solid to behave like a liquid. The Chinese engineers at companies like Qingdao Energy, WeLion, and the research institutes backing Geely and Dongfeng looked at the problem and completely reframed the substrate. They did not try to build a perfect ceramic. They built a hybrid, and they changed the state of matter inside the factory. Let me walk you through the mechanism, step by physical step, of how they bypassed the 3 walls that stopped Toyota. Step 1. The sulfide polymer hybrid. Instead of using a brittle oxide ceramic, Chinese labs pivoted heavily towards sulfide-based solid electrolytes, combined with a polymer matrix. Sulfides have an ionic conductivity that rivals liquid electrolytes. They let the ions flow almost as freely as water. But sulfides are softer. They are more malleable. This solves wall number 1. The softer solid can be pressed tightly against the electrodes, creating a near-perfect physical contact and eliminating the interface resistance that choked the early prototypes. Step 2. In-situ solidification. This is the manufacturing masterstroke that bypassed wall number 3. Instead of trying to manufacture a perfect, brittle ceramic sheet and then painstakingly stack it between electrodes in a billion-dollar dry room, they inject a liquid precursor into the battery cell. This liquid flows perfectly into every microscopic pore, just like the old flammable solvent. But then, through a precise chemical catalyst and a controlled heat cycle, the liquid cures and polymerizes. It turns into a solid gel polymer right there, inside the sealed cell. They use the liquid to achieve perfect contact, and then they freeze it into a solid. The manufacturing footprint collapses. You can use modified versions of existing lithium-ion gigafactories. Step 3. The pure lithium metal anode. Because the new solid polymer hybrid is tough enough, and because the in-situ curing creates a perfect, gapless interface, the battery can finally handle pure lithium metal. They strip away the heavy, bulky graphite hotel. They replace it with a microscopic foil of pure lithium. And here is the brilliant part. The 3 old weaknesses of the solid-state battery: the interface resistance, the dendrite shattering, the dry room manufacturing costs. They do not get fixed. They disappear because the substrate changed. By moving from a rigid ceramic to a curing sulfide polymer hybrid, the material adapts to the electrodes instead of fighting them. The result is a cell that achieves 400 watt-hours per kilogram. That is not a marginal improvement. That is a 33% leap over the absolute physical ceiling of the best liquid lithium-ion cells on Earth. That is the difference between a car that dies at 600 kilometers and a car that drives from London to Rome on a single charge. But a chemistry breakthrough in a university lab is one thing. A car rolling off a mass production line is another. And this is where the story shifts from a clever reframe to an industrial earthquake. Let us look at the hard, verifiable deployments happening right now, in 2026. First, Geely, the automotive giant, has integrated semi-solid and solid-state cells into their premium vehicle lines. The numbers are staggering. 400 watt-hours per kilogram of energy density, a verified range exceeding 1,000 kilometers. And because the electrolyte is solid, the battery passes the nail penetration test, the most brutal safety test in the industry, where a steel spike is driven straight through the center of the cell. A liquid cell explodes into a fireball. The Geely solid-state cell does not smoke. It does not catch fire. The voltage simply drops. The fire is dead. Second, Dongfeng motor. In the second half of 2026, Dongfeng officially initiated mass production of their solid-state battery packs. These cells operate at 350 watt-hours per kilogram and are slated for deployment in their next-generation electric fleet. They are not waiting for 2030. They are shipping them now. But the most critical proof of scale is not a single car company. It is the national policy layer. In July 2026, the Chinese government released the world's first comprehensive national industrial standard for solid-state batteries. Read that carefully. They are not just funding research. They are writing the global rulebook. They are defining the testing protocols, the safety metrics, and the terminology for the next century of energy storage. When China sets the standard, the global supply chain aligns to it. The capital deployment behind this is immense. The state is pouring tens of billions of yuan into the solid-state supply chain. Companies like Qingdao Energy, which backed Great Wall Motor's early deployments, and WeLion, which supplies NIO, have built gigafactories specifically designed for the in-situ solidification process. They are scaling from megawatt-hour pilot lines to gigawatt-hour mass production, and the market is responding. The global automotive supply chain is realizing that the Chinese solid-state timeline is not a PowerPoint presentation. It is a physical reality. While Toyota is still tweaking ceramic prototypes in Japan, Chinese consumers are driving 1,000-kilometer cars that cannot catch fire. This is happening right now, today, in 2026. The 5-year joke is over. The industrial ramp has begun. But here is the honest part of this story. And I want to be straight with you, because this format does not do blind hype. The solid-state battery is a monumental achievement, but it is not a magic wand that instantly renders every liquid battery on Earth obsolete tomorrow. And pretending otherwise ignores the brutal physics of mass manufacturing. First, there is the reality of the breathing anode. When pure lithium metal charges and discharges, it does not just sit there. It physically expands and contracts. It can swell by up to 300% in volume during a full charge cycle. In a liquid battery, the liquid flows around this expansion. In a solid-state battery, this massive physical swelling creates immense mechanical stress on the solid-solid interface. Over hundreds of cycles, this breathing can cause the solid electrolyte to delaminate, or peel away, from the anode. When it delaminates, the resistance spikes, and the battery degrades. Chinese engineers have mitigated this with advanced polymer binders and stack pressure. But achieving the 3,000 cycle lifespan of a standard liquid cell remains a brutal engineering challenge. Second, there is the cost. Today, a mature liquid lithium-ion battery pack costs roughly $100 to $150 per kilowatt-hour to manufacture. The solid-state packs rolling out of Dongfeng and Geely's pilot lines are still significantly more expensive, often double or triple the cost per kilowatt-hour. This means that for the immediate future, solid-state batteries will be reserved for premium high-end vehicles. The $20,000 economy EV will still run on liquid lithium-ion for several more years. Third, the sulfide electrolyte, while highly conductive, is extremely sensitive to moisture in the air. If exposed to ambient humidity, it can degrade and release toxic hydrogen sulfide gas. While the in-situ curing process seals the cell perfectly, the manufacturing environment still requires stricter environmental controls than a standard liquid cell factory, keeping the capital expenditure high. None of this erases what the engineering has already proven. It simply marks the distance between a premium breakthrough and a ubiquitous commodity. The 1,000-kilometer range is real. The fireproof safety is real. The national standard is real. The rest is yield, cost reduction, and time. And those are exactly the variables that the Chinese manufacturing engine is most terrifyingly efficient at solving. Which brings us back to the bigger picture this whole story has been building toward. Because this is not really about a car battery. It is about the end of the oil century. For the last 100 years, global geopolitical power has been mapped directly onto the geography of liquid hydrocarbons. Nations rose and fell based on their access to oil. Wars were fought over pipelines. The entire architecture of the 20th century was built around the flammable liquid. The transition to electric vehicles was supposed to change that. But it was hampered by the flammable liquid inside the battery, the range anxiety, the charging times, the fear of the fire. These were the psychological tethers keeping the world dependent on the gas pump. The solid-state battery severs that tether. When a vehicle can drive 1,000 kilometers on a single charge, the concept of range anxiety ceases to exist. You charge it at home, once a week. Just like you charge your phone, the gas station becomes a relic, and the country that controls the patents, the manufacturing standards, and the supply chain for the solid-state battery becomes the new Saudi Arabia of the electro-century. In July 2026, China did not just release a battery. They released the national standard for the technology that will power the next 100 years of human mobility. They took the holy grail that the West and Japan said was impossible to manufacture, reframed the chemistry, bypassed the ceramic bottleneck, and put it on the road. The world that ran on oil did not announce its own ending. It just started losing ground to something that cannot catch fire, cannot be embargoed at a pipeline, and drives 1,000 kilometers on a single charge. So here is the question I want to leave you with, and I genuinely want your answer in the comments. When the fundamental limitation of the electric vehicle is solved, and the solid-state battery becomes as cheap and ubiquitous as the liquid one is today, what happens to the geopolitical map of the world? Which nations rise, and which nations fade into history? When the flammable liquid is no longer the currency of power? Drop your answer below. I read every single one. And if you want a front row seat for the next time an impossible technology quietly rolls off a mass production line, hit subscribe. The next decade of this story is going to move faster than anyone expects, and you are going to want to be here for it. I will see you in the next one.